Today we're gonna do folding, which is essentially distortion. I'm not gonna. Well, I have to say a few things about what it does, which you might know, but and then we'll get into testing some of these. I've squeezed most of my folders in this rack, and so we're gonna look at what they do. Actually, also be listening to them, and then we're gonna dig into building our own, similar to the compression class. I have a few lined up. Maybe I should announce them as a wishful thinking. Things that I would like to do in terms of building. So first of all, we're going to try to build a kind of sample rate reduction, essentially. So obviously it's a digital thing, so it's not sample rate induction, it's sample rate, no, not deduction, but induction, because we're going to make it a digital signal, so to speak, which is kind of the other option from bit crushing. Yeah, so bit crushing is your kind of vertical quantization, and this will be horizontal time-based. Then we're going to look at distorting tails, because normally the transients are the ones that get distorted. Hopefully then we build our own clipping, then we hopefully build our own folding from that, and then hopefully build some subharmonic folding as well. Hope we get there. Okay, so I've shown you in the very first lecture the kind of demonstration of the transfer function. Yeah? So what you do with distortion is essentially you induce a nonlinear transfer function. So should be drawing these things as well. Give me a second. So what you have with nonlinearities is that they will induce further harmonics. Yeah, so that's the crucial thing. Nonlinear distortion is famous for essentially suddenly creating new partials. Okay, so what you expect from a nonlinear distortion, that's actually the technically accurate term, normally I just call it distortion, is that if you put in a sine wave, you will get some harmonics. Yeah, that's the basic thing. Now, what happens, how do you do this? Well, essentially you have a transfer, which is, well, this is clipping transfer. Yeah, so just so we understand this is the input axis, this is the output axis, and what you get essentially is a linear transfer in a certain region, and then you get essentially no transfer. You're stuck. The output signal will not go above a certain level, whereas obviously the input signal keeps increasing, and similar thing in the negative portion. Yeah? So that's your basic clipping. And then from here what you get is all kind of folding, which we will look at today. So instead of just having a flat line, in terms of let's take a sine wave, okay, so we see the waveform. So instead of having a kind of flat clipping, what you actually get is some kind of folding here. It could also actually go multiple folds there, and so on and so forth, and you'll see the difference between these modules. Okay, so that's the program for today, and well, let's get going. I've shown you how you can actually display with an oscilloscope the actual transfer function, the full range transfer function. And I did this by taking a sawtooth wave which goes between -12 and +12, so we actually have the full range, and for each of these incoming voltages we see what is the output, and that essentially plots that. I don't have a sawtooth wave in this rack, so we won't be looking at the exact transfer function, but nevertheless we will see what is going on. And the nice thing about these nonlinearities is that we can actually do them in control rate. Okay, so here is my fairly slow triangle wave, and because it's a frequency independent process, what it does, it just changes the amplitude essentially, independent of what the frequency is. Therefore we can actually fix it in control rate, while we see how the things move about, and then we can input an audio rate signal and distort that. Okay, so that's my basic triangle wave that I'm going to be using today. I'm gonna... Okay, so first thing is distortion wave shaper. It's a fairly simple one. I'm gonna go through these now briefly, and this is what it does. Okay, so I'm sending this triangle through, and I have a few controls. I essentially have it's probably good to draw it so you guys can see it, what it's supposed to do, because it's not just a clipper. It can act as a clipper, but it can do a bit more, because what it says it does, and that's what we're going to verify, is that it takes a transfer, yeah, and then it actually has plus level control, so kind of where is the threshold for clipping, yeah, so it has plus level and minus level control, okay, and then it has this A control. I can't quite remember what it is supposed to... Am I doing this right? Yeah. What is it supposed to do, the A letter? But essentially with minus A control, what I can do is control what happens after the threshold, in terms of, am I just gently kind of saturating it, am I actually clipping it, or am I getting into the folding phase, and the same here for plus A. Okay, so that's what we expect to get from this one. So let's see if we can do that. So I'll set the plus A to 0, and the minus A to 0, so we expect it to be clipping, and then setting the levels, the plus level, I can take it possibly a bit lower. Does that do the trick? Minus level, okay, and the A needs to be 0. Okay, so this is my amplification. Okay, so do I get the plus bit? Hey, let's see. That's funny. It actually does not really. Okay. It seems that I've blown this one as well, to be honest. I had a little accident earlier. Let's just hear what it does in terms of sound. Maybe that will help us. Okay, so this is my sound here. Because I noticed that these controls didn't quite do much. So this one does something. I'm just checking. Yeah, my minus A and plus A don't seem to. I think that's the overall. I'm afraid it looks like indeed. Oh, this one is now doing. Okay, it must be me. Okay, back to the drawing board. Let's see what it does. Lower this frequency down. So, you see, you never even know your own modules. Because we did get this. See, could it be? Let's try to do this audio rate. It's not supposed to behave differently at DC rate, but it might be the case, so let's just take the audio rate instead. Okay, so here we go. So the minus level goes up, plus level, yes. Okay, there we are. Okay, so now the plus A should give me some folding, but it doesn't really. Oh, there we go. So we do get some folding. Okay, and then I should be able to get the folding into the negative bit as well. There we go. Okay. So you see, that's essentially what's happening from a triangle wave. Maybe it's useful to display that one as well. From a triangle wave, obviously I amplify the signal quite a lot, and then I get these things to fold back. Okay? Right, so that's this one distortion wave shaper. It's also CV controllable.
And how's it doing it? How does it work?
Well, we'll get into kind of creating our own in a bit. Yeah, so we'll try to do something similar to this. You will see it will be quite tricky to get everything to line up as nicely as this one does it, but we'll get to that in a bit. Okay, so that's this one. Now what I have here is voltage control wave multiplier, and this is what this beast does. So here I would have the number of multiplies control. Okay, I would have the folding level control. Okay, I have the symmetry, which doesn't seem to do much right now. Okay, I have the harmonics. Okay, so possibly if I don't have enough multiples, these other two won't do much. Let's see, folding level. Okay, right, so actually this is my harmonics control. This is what it does. Maybe we can have a better look there. Okay, and then the symmetry does this. So the thing about symmetry, we will test this as well, is that if you have a symmetrical transfer, then you technically get no even harmonics, only odd harmonics. You have to have an asymmetrical transfer to get any even harmonics out of the system. And that's the theoretical backing of that. So there you go, you see it. We can listen to it briefly as well. The thing is that, don't ask me the question, how does this one work? Briefly listen to what it does. Obviously you might want to see that as well, yeah? So this is my harmonics control. This is my symmetry control. It's my folding level. Let's see, because we don't really see the triangle in there, yeah? Let's take the trigger on the first channel. Okay. That's the folding level, and then the multiples. So the nice thing about this is obviously that, you know, I'm demonstrating it by kind of rotating each slider one after the other, but actually you are seeing a four-dimensional space. Yeah, so, you know, it's a very difficult to take one point to make it a space-filling trajectory in 4 dimensions. You know, so you could actually say that, well, we have very little chance of hearing all the possibilities unless we are really kind of meticulous and pick a way to produce a trajectory of a 4D point in all possible, you know, kind of space-filling thing. Yeah. Okay, so that's this wave multiplier 1. Then comes the wave multiplier 2. With this one I can tell you what it does, because this is a slightly simpler beast. So here essentially what I have is 4 shift units, and I have their sum. So you see, it's a less subtle thing. But it does look cool, yeah, as far as the waveform goes, yeah. A bit like Transformers, yeah. Okay, so what this one does, this is actually a trick that is called, I'm gonna come up with this in a second. It is called, anyone knows with the phasers what you do is called? I'll come up with this later, what it's called, maybe. Let me have a sip, maybe that does help. It is called, any cheat sheets around here? Essentially what the trick is, hopefully I'll come up with the name in a second. My afternoon nap wasn't so successful, as you can tell. So what it does, it takes, if you take a phaser, this is how to explain it. Wave, I almost said it. Animation, that's it. It's a stupid name, that's why it's so difficult to remember. I don't know why they use this term. But wave animators, this is a wave animator. And what it essentially does is, with a funny kind of comparator-based circuit, what it does, it essentially manages to shift the phase of a sawtooth wave. So let me try to draw this. Essentially the phase becomes different. Yeah? And the way it does it, it uses a comparator to essentially cut off this bit. Yeah? And then this bit is then pasted down here. You see? Because this is this triangle here, that is beyond the boundary, and if you obviously cut it, I won't go into the circuit here, but that's the technique. You essentially offset it down, which means that you get the same triangle here, and once you connect that, so actually you see that from here you will get this jump here, and then the same thing happens here. You essentially get this kind of, this is the process that's going on. So that's your wave animation. Now, it's a funny process because for a sawtooth wave, it will produce a phase shift. What will it do to a square wave? Huh? Well, I mean, there's two things we can do. We can think about it, but we can also listen and look at it. It's not very exciting for a square wave. I mean, essentially I can shift these levels a bit, but the thing is that there is no real thing happening, because you see with a square wave I am kind of getting a potential phase shift, but it's really difficult because you cannot find this point on this flank in a meaningful way, because there is no such flank. It's just straight up and straight down. So this kind of process indeed is interesting, more interesting for non-square waves and other things as well. Actually, so far I've been changing the amount of certain shifts. Actually, if I take them all to 0, but I can also control the amount of shift. Oh, sorry, that's not something I meant to say. Okay, nice thing about this module actually is that you can hack it. I didn't hack mine yet. You can take the output of different shift units separately. So it can act as a bit of a more powerful thing. Okay, next up I have this type of folding, which is the one that I've shown in the first lecture briefly. And the funny thing here is that you can get your folds where the 0 line is, you see? So obviously now I'm folding the triangle wave there, and you see that the top aligns with this top, the bottom aligns with this bottom, and actually the point where things are going wrong is just around the 0 line. Yeah? But I can make it around the positive, the negative. It's a nice one because I can increase the amount of folding stages like this. And it has these two controls, symmetry and folds. Okay? So you see that there's many kind of things you can do. I mean, if you have some inspiration in terms of, you know, maths, transfer functions, you can do quite a lot. But I would like to now briefly talk about what it means. I think we've touched on this briefly in the first class. What it means that I am folding the wave around the zero line rather than folding it at the extremities. Well, first of all, the transfer function will have its nonlinearity here around the zero line, and something like this should be the transfer of what we've just seen. No? Now, in terms of how this affects the sound, it will distort everything, because actually, no matter that whether you have a loud or a soft sound, they all cross the zero line. But the nice thing is that it will not have this prevalent distortion on loud bits, because normally if you start doing your folding or you do your distortion kind of thing here and here, then the soft sounds will actually go through a linear transfer and will not be affected really. No? So that's the kind of thing. So let's go from here then to what I mentioned as our second target. It's to distort tails, because that's now timely. So what do we mean by this? Because you see, with this type of distortion, actually it might be worth just making a little percussive signal and kind of keep distorting that, so we hear this dependence on the amplitude. Yeah. So I'm gonna take this sawtooth wave and just possibly another sawtooth wave, a square wave, okay, and run a. Can I do this? I probably can. I will run a square wave, a slow square wave into my VC slew processor. Yeah, so lagging. So I will get kind of length from the square wave. Probably best if I look at this before I go further. So what I'm trying to do is take a slow square wave. Okay, and I already get a kind of attack release type thing happening. I'm just going to exaggerate that a bit more. Maybe slightly lower frequency there. Okay. So that looks okay. Let's just see what is the overall. Okay. So we get kind of a varying amplitude, and then I'm going to multiply that signal with the audible frequency. Okay, audio there, and then it should sound a bit like this. Okay, so I'm gonna take, well, first of all, a triangle wave, so we hear the distortion better and possibly lower frequency. Okay, so CV. I'm clipping here a bit. Okay, so we have this signal. So just to make the point that I was trying to make earlier, is that if I take this kind of signal through my folding here, I am bound to get bit weak, this one. Oh, no, that's stupid. Second input, okay, and then want to listen to it. Okay, so what you get here thus is that the harmonic structure in terms of the distortion. So when you do the nonlinear distortion, you produce harmonics in a certain kind of fixed structure. But because this distortion is next to the zero line, you get that the harmonic structure depends on the amplitude. So actually this behavior in terms of changing the kind of harmonics you're creating based on the amplitude is the feature of this kind of folding process. Yeah? So we can just to check how do the other folders deal with this. So this is my animation. Okay, this was my wave multiplier. Point, and then this is my initial clipper with a bit of folding potential in there. Okay, so how could we then make it such that the soft bits get distorted more? This is a kind of a holy grail in terms of distortion. Any ideas? Well, we've done something similar. So what we can do, obviously we won't be making these funny transfer functions just like that. I'm going to get there, but you will see it gets quite complex. But what we could do based on what we know so far is we can take the amplitude signal. Yeah? So if I have the amplitude signal, which is currently this, what I can do is make sure that from this one I derive a signal that goes a bit like this, because all I need is a signal that will tell me when this thing is soft. Yeah, because then I can say, okay, when this thing is soft, then I'm gonna do something. So you see, that's how you can think about these voltages. They actually represent.
So you use a comparator?
Yeah, we can use a comparator. Yeah. So let's see if we can get that done. So first of all, now I'm gonna have to start to make a bit more sense. So this is the input signal. Which one is the input signal? I'm monitoring two things. Okay. So what you see here, did I swap them around?
So with your comparator, can you have it look at a signal and then select another signal when it's at a certain value, or does it always just send out the same?
Comparator will only give me 0 or 5 volts.
Right, will it? Okay.
Yeah. So there is no way around it.
Just a binary.
Yeah. But that's what I'm going to get into, because we can actually do some funky things with that anyway.
But then you could use a VCA or something to.
Yeah, exactly. Yeah. It's worth mentioning that, you see, in a kind of continuous system, that's the technique that we'll potentially use now, but definitely towards the end of this class, is the switching. Yeah? Because I do actually have a switcher, which is a kind of a simple thing, you know, you have one input, two outputs, or the other way around, and then you have a way of changing the signal flow. But actually the other way of doing switching is by using two gains and one summation. And what you do is you take your signal and you multiply it with a 0-1 signal, with a kind of a square wave signal. You see? Because what I can do here, for example, if I have a single, let's call this input signal, it goes to these two multipliers. Now the square wave that I use in this multiplier should be such that I have unity gain and infinite attenuation, muting, okay? And then for the other side, I would have the exact same wave inverted. So in this case, it would look a bit like this, and so on. Okay? So if I have an inverted kind of pulse wave into gain stages, what I can do then is essentially take this through process A, whatever that may be, take this one through process B, I can sum the two signals, and then I essentially get a situation whereby I've processed different parts of the signal in different way, but it remains continuous. You see, it looks like a funny sketch but the point is that you see when this one is giving me 0 volts, it means that there is no signal coming through the left branch. And if this one is in sync and inverted, what you get is that those are the moments when I do get a signal out of this branch. So it acts a bit like a switch in that you either have signal through left or right branch and never simultaneously. Yeah? So it's a kind of a second way of getting a kind of a continuous circuit switch. Okay? All right, so back to this thing now. What we have is a nice little whoop-a-doop-a-doop sound, which sounds like this. Say sound like this, okay? And then what I'm gonna do is I'm gonna take it through my amplitude follower. So lucky I have it here. Yeah. And let's look at the amplitude signal. So there you see the... Okay, so that's my amplitude signal. I mean, I've synthesized it using this signal, but let's assume that, you know, I don't have the luxury of having done that. See, so that is my amplitude signal. By adjusting the gain, I can kind of change the way it responds. But you see, actually, there's quite a bit headroom there. Okay, and then now I'd have to do my comparator magic and hopefully get the type of signal that I drew earlier. So a signal that will actually jump up at some point when my envelope is low. Okay, I'm gonna keep displaying this envelope, that's quite crucial. And then we go into the comparator, and then let's look at the actual comparator output here. Okay, so see, so there is some sync there. So what I get here is the exact opposite of what I was wishing, because I wanted the signal to go up at the moment when the input signal is very soft. The nice thing is I have an inverted comparator output as well. Yeah. So that's kind of getting there. So what we would want from this is potentially a bit of lag. The problem with that is that I have not any lag here left because I'm using this one already. But it's a useful thing because I realized a bit too late that I forget to show you how low-pass filters can do lagging, although we've talked about it. So, and I'm left with only a few here. So let's see how they cope with this task. Can we get some lag out of this one? So audio level emphasis, comparator out, frequency. May have busted this one. Let's try this one. So that's my input, this is my low pass output, hopefully resonance level frequency. Okay, so you see this is the filter response on my signal, but it's not quite doing the lag that I wish it did. Okay, let's try this one, I have a few left. Okay, this one is resonating a bit crazy. Okay, so you see this one at least preserves some of my DC offset, which looks promising. Okay, so you see that I can actually get my original wave back, and then by reducing frequency I hope to you see this is the filter that can actually do this for me, give me a bit of a smoother thing there. Okay, so now I've got this. What I would like to do is take the original signal that we started with. Okay, so that's the one coming out of here, which is this. Okay. And then I'll take the same signal and distort it. Well, first of all, I'm gonna make a version with a VCA. I'm gonna make a version that actually takes only these bits. Okay, so this is my signal. Just a sec. I hope I don't get horribly confused already. So this is the signal.
So I'm just going to take your comparator into the...
We're going to draw this patch in a second anyway. I think it'll be worthwhile. But now what I'm doing is I'm taking my comparator through the low-pass filter, to get it a bit smoother.
And then into the VCA.
And then into the VCA, exactly. So this is my input, and this will be my VCA control.
And you'll just use that to trigger your output signal.
And then I'm just going to first get to hear it, hopefully. That what I get here is... So this is my... Sorry, actually I should do this like that. Okay. So this is my secondary signal. This is my original. And then what I can do indeed is say, okay, now that I've isolated the soft bits in my original signal, what I can do is distort only those soft bits. Let's see, is this doing the thing? The thing is, I have a bipolar VCA here. See, so now I'm sort of there. It's not really clean in terms of the cut. And it seems I'm getting the most response actually from this flank going up. But now I can do funny things because now I have a filter in the circuit. I can get that to self-oscillate. Cool, so let's draw this patch. Yeah, let's see how much you followed. Grab a paper. I have a few papers here as well. And then we'll go on from this. Does anyone feel like drawing it, or am I just doing this? Okay, draw it in your head.
So I've got the end bit. I can't remember the first bit. So I've got the bit when you're coming through the filter.
You wanna draw the circuit? Yeah.
So you've got the wave coming into the slew.
First, I've got... Well, let me not confuse it too badly, because actually I have a few modules that are responsible for getting the synthesized signal. So I'm not going to draw that because it's going to grow quite rapidly. But instead, I'm going to just call that a single block, which is my signal that did this. It was loud and then it was getting softer. Yeah, so that's my input signal. Okay, so from here, what we did is we've taken this to the envelope follower. first, yeah? So we get the signal that follows the envelope. Then we've taken it through the comparator, CMP. Okay, and from that we had a signal that did this, which actually gave us positive values when this one was soft. Then what we've done is oh sorry, that's wrong, because it's a strictly 0.5 volt signal. So we had this beast, yeah, very cornery. Then we've taken it through one of the low pass filters, and you've seen that two of them didn't quite do the job, and then I found the third one which did, and that did the job of making these corners a bit smoother. Okay, and then we've taken this to a VCA, which was fed the original signal. So from there we had essentially this, and then we've taken that and just did a folding on it, and then we mixed that together plus with the original signal back again. And that's when we got, so after the folding obviously we got this with a bit of messy tail, and then in the end what we have is something that is a bit like the original signal, but at the soft bits it goes crazy. Yeah?
Was there an inverter after the comparator?
I've taken the inverted output of the comparator.
Okay. Yeah.
Very good call, indeed. I'm probably best off highlighting that as well. There is an inversion here, maybe just an I here as the inverted output. Yeah? Cool. So you see, actually, you know, at this level you can really build these things in funny ways. Okay, so I'm gonna remove most of the things except the original sound, because that one might be useful. So the folding goes, this filter goes, the comparator goes, and the mixer goes for now as well. Okay, so next up, let's look briefly at sample rate downgrading, or in this case obviously the induction of a sample rate. Let's look at essentially quantizing our signal in terms of time points, and the way we do this is using a sample and hold. Okay, so what I have here, let's see, is this same audio signal. Hello, audio signal. Okay, and then what I can do, let's keep looking at it as well. So this is now in the second channel. Sorry, that's now in the, yeah, in the first channel indeed. Okay. Zoom in a bit so we see what's going on. Sorry, that's not what I meant. Okay, so that's my triangle with this envelope. And then what I can do is, if I take this signal into my sample and hold, what I need to do is drive the trigger input of sample and hold with a fast square wave. Okay, and then I should be able to get it distorted. Okay, so what you see here is that my triangle that I had a second ago got a bit truncated. I should be able to show you both. So that's the original, and then that's the truncated one. So actually what sample and hold does, it takes two inputs. One is the voltage input and the other one is the trigger input. And from these two signals it produces what you've just seen. So what it does is voltage signal comes in, whatever it is, and then the trigger signal comes in as well. It could be a regular signal, but it doesn't have to be regular. Okay, and then at every moment of the trigger you sample the input signal and you get a stepwise function based on these sample points. So this is essentially your analog to digital conversion. So that's what I'm doing here, and that's what you can see or hear. So if I change the frequency of this square wave, thing is that I have the same control for both things here, which is a bit unfortunate. This is the triangle wave, okay? Yeah. You see, so actually at some point... Oh, sorry, it's not meant to do that. You see, I almost get a clean thing out of it. Oh yeah, and I've increased the frequency of that as well. Okay, I'm just fiddling because I have this single oscillator, kind of single control for everything. So if I do... Okay. Okay, so that's your essentially A to D conversion. And the thing to know is that this will produce aliasing effects, and the aliasing partials, the aliasing overtones will not have a harmonic relationship to the input sound. So the thing that we had with clipping and actually folding as well is that you had a harmonic relationship to the original sound in terms of the new components that are induced. But what you get with aliasing is that the sampling frequency, the half of it acts as a mirror. So everything that wants to reach above that frequency will be folded back into the spectrum. So you get kind of this spectral nonlinearity. And that's why you can really quickly hear it as a kind of a separate sound. You see? Where were we with this? Whereas with the others it is more kind of shaping the original sound rather than it being truly separate. Yeah, so it's a more kind of harsh thing happening. Okay.
No way to get that to be in tune still?
Well, I could tune the sampling frequency
you can.
to, but obviously this is if I have multiple frequencies. I mean, if there is a harmonic relationship between the input signal and the sampling frequency, then obviously the aliasing components will have a harmonic relationship to the original as well. But it kind of breaks down nicely once you get below, you see, because if I get my sampling frequency to be below the... See, now the original is this high frequency, so now if I go with my sampling frequency below that frequency, see, now I'm actually getting only aliasing. Yeah, because this sampling is way below the other one. Okay. Yeah, is that cool? Okay, so now we're supposed to get into the difficult bit. How are we with time?
10 to?
10 to 8. Okay. Which actually, that's great news, because it gives us a lot of time for me to get confused and to confuse you as well. So what we're gonna try to do now is build our own little clipping and filtering thing. So I'm gonna get rid of all of this because we're gonna just work with a single triangle wave. Please do. And the way we're gonna do that is using a comparator. So maybe it's best if we just first design it, yeah? So how can we make and to start with, I'm gonna just do a clipping on one side of the signal, just to keep things simple, and to be honest, to keep things or make things asymmetrical as well. Okay, so we start with the triangle wave. And what we want is to clip it like that. And what we want as well is to be able to control the clipping level. Any ideas?
You could just, depending on what modules you know, you can just turn the gain up loud to the point that the op amps don't handle it anymore and they're rail to rail.
Yeah? Shall we do this to start with before we get into the stupid ways of doing it? Because actually that's a good one, except for a symmetrical bit, but maybe you can come up with a solution for that as well.
DC offset?
Yeah. DC offset back and forth, and you get it asymmetrical. So let's do that first. So here is my triangle. Let's look at the waveform. Okay. Well, actually, let's keep it control rate. Okay. So what you've suggested is gain the hell out of it.
Yeah.
Now, it's not always simple, that technique to do. That's why it's interesting to look at. So I have here a VC polarizer that's supposed to give me more than unity gain. But if I look at it, if I take the gain full up, well, actually this one is decent. There you go. I'm a bit of clipping already. But the funny thing about this one is that actually with a CV DC signal, what I can do potentially is make it clip even worse. Yeah, there we go. So that's even more clipping. And then what I can do is I can take it through another gain stage. Okay, and then I get even more clipping. And then I can put in yet another DC for this for the gain amount to clip it even more. Okay, so this is kind of a lot of clipping that I can get out of this, and then obviously I can attenuate it back to get to the original type thing. So let's do that as well. Out there, in here. Okay, this is unipolar. Okay, so now I take back the amplitude and I get a clipped signal. Yeah, so that's fairly straightforward. And then the thing about making this asymmetrical, what I would have to do first is before I get into the into my gain stages, because I've made it a few actually, I will first offset the original signal. Okay, and then get into this gain stage. Okay, so you actually see that happening already with the amount of offset. This is what I'm getting, which is really cute because I'm essentially getting a pulse width modulation. Yeah, I can decrease the amount of gain in my gain stages. You see now I'm kind of out of the clipping range. Get this kind of behavior. Okay, want to listen to that as well? let's see, obviously need a decent frequency for that, and then my final thing was actually this. Okay, so with this DC offset, let's keep looking at it as well. Okay, I've removed the looking at it bit. Just a sec. Channel for the trigger. Okay, so now with adjusting the DC offset before all these gain stages, I can get this. I can push the gain up further the way it was. So I'm almost getting a square wave there. Okay, so that's the first thing. Yes, indeed, we can cause clipping like that. Technically soft clipping, and then, you know, depending on how harsh it is, you actually get very close to hard clipping as well. But let's get back to our sketch and think about how to do this with a comparator.
Well, yeah, it's pretty much what we did before, wasn't it?
Is it?
Run it for a VCA and then...
Well, it is a similar thing.
That's what I mean.
Yeah, I can't quite recall if it's going to be the exact same thing at this stage, but it's definitely a similar thing. So what we're going to do is we're going to make a switching network. So I've shown you this switching previously, yeah? But I actually have a voltage controlled switch which functions just fine. So what I'm going to do is take this triangle wave.
So your switch just has a threshold, does it?
Yeah. So I take the triangle wave, I take it into my comparator, which will give me from a triangle wave like this, it will give me, well, what am I after now? I'm after the tops. Yeah. So what I'm after is a signal that essentially isolates the tops. Okay. And then I can use this comparator signal straight into my voltage controlled switch. Yeah? Because now if I take this triangle wave into my voltage control switch together with this one, what I get is two outputs, and one of them will be the triangle wave without that top. So everything else is fine, but the top is missing. It drops to 0 when the top is happening. Yeah? And then the other side of this output should be the triangle wave, whereby only the top comes out. So it's a bit like this. You see? So actually I'm splitting the signal using the comparator and a VC switch to get two portions of this triangle wave, but that's still not the clipping. So how do we go to clipping from here? Well, actually, if you look at it, what we need to do is take this comparator signal. See, it's not quite the same thing. If we take this comparator signal, we actually don't need this signal because we are trying to remove the tops, so why keep them? So we're going to take the comparator signal and actually add it to this signal, because the comparator signal would be exactly those bits that are missing, but with a flat top. You see, so instead of putting back the bits with the rooftop, we're going to put in bits with a flat top. So the sum of these two should give us a nice.
You don't really mean your second output, though, do you? You mean the first output? Just as slightly confusing. The VCS.
VCS?
It's the same output, the red and the green.
Oh yeah, exactly. Yeah, this is now the same output. Yeah, I've erased the other output. Yeah. Cool. See if we can build this. Okay, so we have a triangle wave. We have much more here. So let's go back to the basic triangle wave. Why do I have all of these things? I must admit I feel a bit distracted today. Oh yeah, that's because we've done the proper clipping through reaching the rails. Okay, so back to a simple triangle wave. Hopefully. So that's the listening cable. Yeah. So this is my triangle. Then I take this triangle through my comparator. And then the output of that, let's plot this as well. The output of that we can tune by changing the offset, you see? So I can actually do this kind of selection of things. Okay? So now I need a signal that has this inverted comparator as the VCA control. Yeah, to get everything but the tops. Okay? So I'm taking this inverted comparator signal now into my VCA, and I'm taking the actual, oops, I might be losing, here you have to switch these two up. So I have the original signal in there, and then from that what I expect to get is everything but the tops. Okay? So the kind of thing I drew. Now the funny thing here is that there is some anomaly here which has to do with this gap parameter, which we can use in a second. I'll tell you about it in a bit. But now let's just first get the clipping. Okay, so I've removed the tops right there, and then I want to add to this signal the actual value of the comparator DC. Yeah? So the real way to do this is to make sure that your comparator DC is the one that you're adding rather than the output of it. You see, because the output of the comparator is always 0 or 5 volts. And in this case, I haven't drawn a control signal for the comparator because I have it on a dial. But actually what you normally do is you take a DC signal to control the threshold for your comparator. Okay, and this is the DC signal that I should be adding in here, because then if I change the clipping value, I'm changing the actual replacement, the top replacement value as well, and these should work in kind of tandem, in sync, without any anomaly. So let's try to do that. So I've got the, I'm bound to get confused here anyway. So I've got the kind of no tops signal, yeah, that's there. And then I just make sure that instead of using the dial, I will use a DC signal, which I can reuse then to add back into things. Okay, so here is my DC signal for the comparator. Okay, so I can still get the same thing. I can get the tops to get lost. For some reason this gap is still a bit funny. Okay. Right, and now I could potentially add this DC signal to the resulting roofless triangle, if I may. So I'm taking that roofless triangle, taking this and adding it back in. So this is now my, okay, so you see I actually got a kind of folding already, but I should be able to, let me think what I'm doing here. This is the amount of DC signal. Oh yeah, well I've messed it up because I cannot just add the pure DC signal, can I?
No.
No.
But I thought I wasn't going crazy.
No, it's good. I mean, you see, I'm demonstrating the way of getting out of confusion. That's the topic of this course. Okay, so I can't add this DC signal purely because I need it to be only the tops. Yeah. So what I can do here is.
Isn't the output from your comparator the tops?
But it's going to be only 0 to 5. So actually, what I'd have to do is multiply these two.
Okay.
Yeah. That's the real thing. I do have another multiplier. I just don't know if I have enough brain cells for that.
And that just gives you the adjustment, you mean, so you can adjust it up and down. So.
Yeah, exactly.
Yeah.
Well, the thing is that you see, what we're trying to do is produce the controllable clipping like that, which makes it exciting. And we're getting there, which is also cool. So instead of just the DC signal, I will. Was this my DC signal? Yeah. I will multiply that DC signal with the comparator output, and actually probably the inverted comparator output. Is that it? Yeah, the inverted one. So inverted comparator, and then add that back in. Okay. So now if I change the value of the comparator signal, some things are happening. Okay. Oh, that's the amount of that signal. This might not be manual. Okay. Manual needs a 0. I'm probably getting really cool things in the meanwhile. You see, the mother of invention is error and confusion probably as well. So the amount of the comparator signal. Okay, now we're doing something cool. Okay, so I think it's better if we just listen to this and forget about it being really accurate, because I think we're getting some cool stuff here already. This is my listening. So if I now play with
the inverted signal.
I'm not sure that I've done the right thing here. Obviously,
the inverted signal.
Oh, is that the? Is it?
I don't
So,
know
oh yeah, it's not the inverted signal. That's what it is. Okay, so let's do the not inverted signal.
Yeah, there you go.
That's better.
There you go. Fine.
I need you here so badly, you see. So you see, I get a kind of a clipping thing. Now the funny thing is, obviously, I'm not listening to what I'm showing you. Do I have another cable like this? Handy. Okay, so this is now the same what you hear and listen. Okay. And then with this, I could potentially. This is not gonna be it. I think you see it's a bit late, that's why it overshoots. But that's quite cute as far as I'm concerned. The thing that worries me more though is the fact that the output has a DC offset that is variable throughout the patch. So as far as a decent clipper goes, I don't think we've quite made it. Yeah? Cool. So there are other ways of doing this as well. So I've gone a really long way here. Let's now do it in a simpler way. We have a thing called min-max. So instead of all this trouble, what I can do is I can take my bloody triangle, take it into min-max, which is mm. I don't know if this reads mm. And just put in a DC voltage there, and I'm done. Okay. This is supposed to be the cathartic moment when you go, oh, that's great. So to hell with this complex comparator business. There is one thing though, if we, it's a bit funny because actually this was the first thing I tried out today, and I got it working instantly. So there you go. And now it's still a bit funny. I didn't get this overshoot. Obviously I won't spend the next hour trying to get back to that state of things. But let's just try this triangle mix min-max trick. Okay, so I have my triangle and I have my... Oh, well, that's great. I don't have this module in here. That helps. Okay, so you know you can do it like that as well. Okay. Right. So we had this kind of clipping, and then actually the thing is that you see, once you have divided your signal into kind of two things, what we had here was the tops and the bottoms. So we had, from a triangle, we had two signals. One was just the kind of rooftops, and then the other one was everything except the rooftop. Am I doing this right? Something like this. Yeah? And so the thing here becomes interesting, because what I can do is I can filter these signals separately as well. Yeah? So what you've seen me do previously is do a kind of lag from one of my filters, so it made the control signal actually smoother, so it's proper low frequency as far as an audio filter goes. Which is something I could do with this as well. We'll try that. But actually the interesting thing is, what you've seen in the compression class, is that I can make these things resonate here a bit. So I can almost kind of induce a little bit of resonance on higher frequency in certain points. Okay, so let's try to do something like that. That could sound quite interesting. So I'm taking my triangle again into a comparator. Okay, so that's in, that's there, and then from here I should have two signals that I send to two VCAs. Yeah, so this is my kind of switching. Or actually I can do it the easy way with just the voltage controlled switch. Let's do it the easy way. So I'm just gonna take this as my input, and then the comparator signal will control the switching. Okay, and then I should get something like this on one output. And it's a fairly slow switching compared to what's going on. How does that work? Probably because of the offset. No. Gap. Hello, hello. Just give me a second. So I made. That's funny. Oh, because this is not that. It helps. Okay. Right. So here is my one half of the signal, yeah, the roofless one, and you see it neatly drops back to zero. You still see that there is a kind of problem there. And then the other one is just the rooftops. Okay? So now I can play with filtering these two signals separately before I join them back together. One thing I can do before I start doing that is just see, is it an accurate thing in terms of summing them back together? Because now summing them back together I should get a clean triangle, and you see I don't. So that's not best, except the fact that we want the anomaly anyway. Yeah. So I've had this, so now what I'm doing is just using this switch, and actually I think that's why the comparator patch is slightly better. I think we didn't have it this bad. So I'm splitting my triangle wave into two, yeah, and then I'm adding it back together, and unfortunately I get kind of an anomaly wherever I produce a switch near the rooftop. Yeah?
And why is that? Because the switch is broken.
Is the switch broken? Yeah, I guess. I mean, as far as the electronics of it go, I think that should not occur, yeah?
It's certainly not to that extent.
Huh?
Certainly not to that extent.
Yeah, that's quite severe as well.
It's weird.
Well, I have these things both full on. Obviously, I can play with these levels. But yeah, that shouldn't quite happen. I mean, I can try the other switch. And it does the same thing. Yeah? But to be honest with you, now that we want to do this funny filtering thing, it might actually be really useful that this is happening, because it will actually launch our filters a bit more. Okay, so what I have here left is this filter. I'm gonna do first a low pass run. That's the input there, the input here. I'm gonna add back the two signals after filtering them just a bit. Okay, that's this one, and then this is that one. Okay. Okay. So now they're set fairly low frequency. Okay, and this one. You see? I have no resonance currently, so just playing with the frequency. If I induce some resonance, I can get all sorts. So now the interesting thing is, I remove the input signal, and instead of the input signal, what I use the output of this process. So I replace the triangle with the output of the whole process and hope that something truly funky happens. Okay. So this now should be capable of giving me some intermittence. You hear the way it's kind of producing a rhythm, it's not quite linear. Okay. You want to turn it's just on the mixer, the monitor level, on this one, yeah? I just want to crack it up a bit more. Yeah, push it. Just on top, yeah?
Oh.
And then left, monitor level. Yeah. Push it a bit for us. Yeah, go ahead, because I'm clipping already. Push it a bit further.
Okay, cool.
Push it up and then, yeah. Cool. Let's see what this baby does. And obviously I have the comparator as well. You see, this is typically a bifurcation point, so suddenly the whole behavior changes. And there is a very kind of little amount of space there available. Which obviously... Because Okay, so there's fun to be had. I had to wake you up because I was like, I'm losing them completely. Yeah, so we had a bit of a clipping with filtering on top, and we should be getting kind of an idea of what it takes to produce the folding. Because now that we have these two signals separated. Question? Was there a question?
Well, I was going to say, it looked like you were folding.
I was folding already, it's just that I unwantingly was folding, that's the only problem. Because I just wanted to do the clipping. But as far as thinking about it, the only thing to realize is that once we've split our signal into the, you know, the rooftop and the rooftop less bit in terms of a triangle, what we've just done. Something like that, yeah. What you really can do, huh?
And then you filtered them, right?
Yeah, now we were just filtering them, and then we replaced the triangle with the output of the whole thing, so we didn't have an input signal. This whole patch now has no input signal. It's a bit like a no input mixer thing, really, no? Because I've developed it with a triangle, and then I just removed the triangle and put the output instead of the triangle, and it started doing these things. Okay, so in order to make a folding, what you initially actually have to do is play with this signal a bit more. So if you invert it, that would be one thing, you know, and control the gain of it and try to keep the offset under control, then you could get kind of a folding thing from that as well. Okay?
And at the moment you've only removed the rooftops, but you could remove the bottoms as well. And
yeah.
Do stuff, so you could have multiple, you know, 3 signals then. And stuff.
Yeah, yeah. I mean, this is just the basic kind of opening up of the whole, you know, how they call it, can of worms. I hope. Okay, so we'll finish by looking at our subharmonic options. Subharmonic distortion is cool. Actually, you've seen me get subharmonic artifacts just from my sample and hold. Yeah, when it's sufficiently low frequency, then it will fold things up and down. The thing is that these were not technically subharmonic. So subharmonic series is the sister or the brother to the harmonic series. So in the same fashion, we have the second subharmonic, the third subharmonic, and so forth. And they are all dividers of the original frequency. So I think, was it the one before the previous session when we looked at one of these? And now I have another one here, so we will look at that one. I'll get rid of this mess first. Because this subharmonic audio divider that I have here is slightly different in that it does not allow me to get to subharmonic indices which are not square of 2. Okay? I've actually said that right. I don't know why I took the trouble. The thing is that if what I have with this one, so with the previous one I had 1 input, 1 output, 1 CV control, and I could get the second, the third, the fourth, and so on subharmonic. With this one, I actually have a mixer between the second, the fourth, the 8th, and the 16th. So this is a kind of different beast. But let's just verify what it's doing. So this is the output of it. Okay, and right, so that's with the original. Now that's all off. I just want to plot the rest of the thing as well. So the actual input signal is this, and I'm gonna show you that one as well. Okay, so that's my input square wave on top, and then the second subharmonic output looks like this. All right, probably speed that up a bit. Okay. But what I have here is actually a way of mixing these. So this is my fourth subharmonic, and then I have the 8th, and so on. But what I can do is I can make a funny mixture of these things. so it looks a bit like this. See, so it's jumping up and down based on these harmonics. Something like this. So what does this remind you from the last class of? And this signal? Pink noise. You remember? It was obviously it's not necessarily random at this stage, but what we had with pink noise synthesis is the need to synthesize variation at different timescales. And this somehow reminds you of that, you see, because you're kind of having a little variation and then a big jump and then a kind of variation at that level. So you kind of get multiple prominent frequencies far apart in the spectrum. Okay, so we have this kind of audio divider. So what we're going to do now in order to produce some kind of subharmonic distortion is essentially go through the same business in terms of getting to the comparator. Okay, and then the comparator signal, which currently looks a bit like this. Let's see the original as well. So I'm taking my triangle again into the comparator. Okay. And I did use this triangle to modify the wave, so I still have it available. So let's do that as well, because we've tried it with a switch and we had the anomaly. So it's a good time now to do it back again with VC. So I have the inverted output and the original one here, and then the input to both things is the exact same signal. Okay, so I can use this one for that. See, I've made these cables with multiple patch points. Okay, so now what I'm getting at is the same kind of splitting, but instead of the switch, I'm using the comparator. So hopefully we will get a cleaner add. So now we're going to add the two split signals back again. Right? It doesn't look too clean yet. So the offset should give us a bit of a... and then I think the issue currently is here, so both full on, manual full down. Okay, are we getting there slowly? Well, it's definitely anomalous, yeah? But I'm not now so much into making this clean. What I'm into at this stage is taking the comparator signal and taking that through my audio divider. Yeah? So in this case I have... It would be cool to have two audio dividers, but because this is now an experimental thing, let's keep listening to the results, because that's what we're after. Okay, it's a bit low frequency. Okay, so now if I change the offset, the comparator DC control, quite cool. Okay, so now what I'm gonna do is I'm gonna take one of these signals and take it through my audio divider, as it's called. Okay. Largely anomalous already. zoom out, there should be some. So now I'm actually doing all the different subharmonics. But you see, now I'm playing with the second subharmonic. I have that only in the comparator, and you see that every other cycle is processed in a different way. Yeah? So this necessarily will give me a subharmonic frequency kind of component in there, the original. That with the fourth one. Yeah, you see, so now it's 2 of the same type and then another 2 of a different type. Actually, the 16th subharmonic, you see, it's already pulsation. Okay, so that's the message that, you know, you can get quite wild with these processes. The thing is that with actual acoustic signals, it's not as exciting, because you very quickly get into just unrecognizable amount of stuff coming through. But with kind of simple signals, sine waves, triangles, indeed you can get quite some mileage out of this. Okay, are there any questions? How are we with time? 25 to, okay, well that sounds like we have some time. My brain is a bit fried, I guess yours too. There was one thing that I really wanted to come to a minute ago, but have I forgotten what I was about to? There's quite a few things you can do. I mean, actually, oh yeah, the racks are now in the back already. I don't have anything in terms of tubes, valves here. But worth knowing is that they typically produce an asymmetrical distortion. One thing we could try doing is do our zero crossing distortion. Shall we try that as the last thing? So let's try to build a circuit where, is this the noise from here? Or it's the...
Oh, yeah.
Yeah, you can pull it down a bit. If it doesn't annoy you, it's fine, but after a while. Okay, so we've had these things when we played with the top, but actually what you have, it's something that happens, I think, with class B amplifiers. I'm not sure which class of amplifier. You're not into that much, no? What happens is that you have crossover distortion, as they call it, or zero crossing distortion. Yeah? So if you have a wave, in the good old boring triangle now, what you get is you get anomalies just when it's crossing the zero line. Because if I have it right, it's a separate circuit that does the amplification in positive and in the negative polarity, and therefore if there is a mismatch, like you've seen us produce mismatches, then you get this kind of zero crossing distortion. So in terms of what it could do, well, there could be two things really. One thing would be, I mean, in terms of the simple things it can do, that can obviously be all kind of anomaly. But the simple thing that could happen is that actually, instead of coming through the zero line, it snaps to zero based on through thresholds. You see? So you get this kind of little staircase just there, and then the rest of the signal is actually fine. And then again, when I get to 0 point, I snap to zero, like this. A kind of zero snapping thing. And then the other thing that could happen, that you can build, could try to build it, my brain is just not there probably for today, is to have this offset compensated for. So what you actually get then is that you go up to the zero line, and then you see you kind of continue. How did that work? You stay at the zero line, and then you continue up, you stay at the 0 line and then you continue down. You see, it's slightly different from this, and especially in that it has less corners, because this one will actually have one discontinuity here and another one here. This one has two discontinuities, whereas this one is pretty much a single one. So this one would be a bit harsher, but we'll play with this one because it's slightly easier to make. Okay, anyone want to project how we're going to make this? It's fairly simple. So what we again are doing is making a way of muting the signal at audio rate, because that's all what we need to do. We have to say that in having this triangle, when the value is less than this, more than this, we actually mute the signal. So what we really need to do here is get a kind of a comparator type signal, which is this, and then we will likely use the inverse of that. So we have the signal on all the time, then we just drop it a bit, we have it on all the time, and then we mute it again, and so forth. Yeah, does that make sense? Okay. So let's see if we can do that. Remove these bits. Okay. So good old triangle into the comparator. Okay, and then the comparator output looks a bit like this. So how do we do this? Well, you see, we're having a problem because the comparator is a kind of a single-sided comparison. Yeah, it tells me whether it's larger or smaller than a certain value, but it does not give me the option to specify two thresholds. Any ideas how can we cope with this?
Can you take like the absolute value of the triangle?
Well, if I was a programming, that would be easy.
I don't know whether there's a...
Yeah, well, actually, we spent some time building full wave rectification, but it wasn't very successful. I don't know if you guys remember that we had some problems with that. Shall we try that first then? Build a full wave rectifier.
Multiplication.
Huh?
We just multiplied it, didn't we? That would be one way.
Well, that would be one way. Let's do that. That's very clever. You see, you're much more lucid today than I am. So what we did actually, which is not full wave rectification, we just squared the signal, which would again do the same thing. So let's try that. Take this triangle wave into both inputs of a VCA. Okay. So that's 1 and 2 inputs of the VCA, and then this is what we get. Okay, so if I just play with this for a bit, I can make sure it looks like a decent squaring. Yeah, so now the whole signal is positive, and now I can take this signal into the comparator instead of the previous one. I will need this one, that should be fine. Okay, so I'm taking this signal now into the comparator, and the output of the comparator is suddenly something that will do the right thing. Okay, so, and then we use the inverted output. Yeah? So we take this inverted output and we multiply the original triangle with that. Okay, something's happening. Let's just get a bit more details there. What I also wish to happen is to have the scope on the triangle. Doesn't quite reach. Can we hack this? What's going on here? We're sourcing. Let's just do the... Oh yeah, that was it. Channel 2. Okay. So what we're doing here is then we have the squaring. Yeah. and we're using a comparator for that, but it doesn't seem to. Okay. There we go. See, we somehow get this kind of two-way thingy happening. It's just that my manual gain here is too much. This one. Oh, wait a second. CV. Oh yeah, there we are. Okay. So I actually have a way of doing a kind of curvature there. We're still a bit loud. Can I? Oh, that's the other one. I don't want to mess with that one. Yeah. Okay. So I have a kind of a zero crossing distortion here. You see? So let's hear how that sounds. This is my signal that I'm listening to. It should be this. Okay. That's my amplitude. See, I get it from a clean triangle. This kind of thing.
And you could kind of filter the squared wave as well to try to then change.
Yeah, shall we try to do that? Yeah, so the CV signal, which is my comparator signal, let's now take it. Now I know that this filter is really good for VC, DC processing. Okay. And then I can obviously try to have some fun. So I have the second output of this filter, and I can put it into the comparator DC voltage. See if that does funny things. See? I get this kind of. If it's hurting your ears, you know where the pot is, yeah? That's a cool graph, yeah? Actually, this all has to do with the fact that my filter is resonating, yeah? That's why I get this nice frequency through that. Can get asymmetrical transfers as well. Okay, how much did this thing do? Didn't quite get chaotic. Let's take it through a folder as well. See, that's always the point where it's most exciting, if I can get it just there before it cuts out. Max, you wanna pee? Okay. You can have fun. She's asleep. That was a sound of a dying mouse, probably. Like, okay, then everything is fine. Mice are dying.